everyone. I think we are now just about ready to begin, so I will start with the introduction. Good morning and welcome. Welcome to our distinguished lecture series on advanced quantitative methods. This lecture series is sponsored by the Partnership for Urban Health Research here at Georgia State University. I am Scott Weaver with the Department of Psychology and the Partnership for Urban Health Research, and it is my great pleasure to introduce today's distinguished speaker, Dr. Judea Pearl. Dr. Pearl comes to us from the University of California, Los Angeles, where he is professor of computer science and statistics. Over the duration of his distinguished career, his contributions to science, spanning areas such as computer science, artificial intelligence, statistics, and the philosophy of science, have been both of great significance and plentiful, and marked by nearly 400 publications in scholarly journals and books. Professor Pearl has much to share with us today, so I will just briefly mention a few of the accolades that his research has garnered. He has published 3 books: Heuristics, Probabilistic Reasoning, and Causality. He's a member of the National Academy of Engineering and a founding fellow of the American Association of Artificial Intelligence. Judea Pearl is a recipient of the IJCAI Research Excellence Award in 1999, the London School of Economics Lakatos Award for 2001, and the ACM Alan Newell Award for 2004. More recently, in 2008, he received the Benjamin Franklin Medal for Computer and Cognitive Science from the Franklin Institute. Professor Pearl is here with us today to share his theoretical contributions with respect to causal inference. It's a topic that I believe, by the virtue of the fact that you're here, that it impacts and is of most relevance to all of the work that we do. So without further delay, please join me in giving Dr. Judea Pearl a warm welcome.
Thank you, Scott, for the warm introduction, and I'm happy to be here. I'm going to talk about causation indeed. That is the field that I spent the past 15 years of my career, maybe more, 20. And I can share with you some results, but more than the results, I want to share with you a conception, overall theme that makes the result flow out automatically, without any effort. Namely, I'm going to present to you a general scheme which is both friendly and formal, so that you can use the mathematics easily to answer most of your questions. And I'm going to make a daring declaration here that every question that has to do with cause and effect can today be algorithmicized or mathematized and reduced to algorithmic detail and get an answer. The answer could be you don't have enough information, but it's still a very useful answer. An outline. I'm going to start with, actually, this is supposed to work, right? I don't need to tie myself to the location. How do I turn this on?
It's okay.
It is okay? You can anyone hear me? Can anyone not hear me? It's okay? I can walk. Okay. My outline will be first to contrast statistical versus causal inference and the distinction between them, very crisp distinction, and the mental barriers that makes us be here today. If it weren't for these mental barriers, then causal reasoning will be as simple as high school mathematics. Unfortunately, something got screwed up in our education that we have to have a special session on causal inference. It should be second nature to every scientist and to every graduate student. I'm going then to present, once we overcome the mental barriers here, we are going to present a unified conceptualization of counterfactual. These are the building blocks of scientific thinking and the building blocks of causal reasoning. Using structural equations and graph, many of you, how many are doing statistical equations or heard about it. Yes, I know many people are good, so I'm going to base everything on something, on the familiar. Then I'll show the fruits of that effort using 3 types of applications. First, finding the effect of potential intervention. Some people call it program evaluation, policy evaluation, fancy names. And attribution, find the cause of effect. And the third one, according to Scott, I should elaborate on that because it is the focus of interest of many of you. It's a question of mediation, decomposing effects into its direct and indirect component. And then frills if we have the time. And then question and answers. By the way, stop me anytime. I like to be challenged. This is statistics, 1 slide. Because it's passé. That's why it's 1 slide. Statistics is the exercise of imagining that you have a model in the form of a joint distribution function and that can answer all your questions if you had it. But you don't have it, so you have to estimate things. Okay? So that Santa Claus spits out data, and your job is to take the data and infer some property of the Santa Claus. Like estimate the mean, for instance. Okay? And if you had the joint distribution in some form, you wouldn't have to go through the exercise. You don't have it, so you look at the data and try to infer the mean, the variance, many properties, some conditional probability, for instance. Here are the tasks that you can answer. Infer whether customers who bought product A would also buy product B. Many people make a good living by just solving this problem. And here is a question, the property that we're trying to estimate can be articulated in as a function of the joint distribution. It's just the conditional probability of B given A. I finish with statistics. That's all we need to know. But that, of course, Q can be very complex. The number of variables here can be very large. They can be very temporarily, a long time, with noise, with all kinds of things. But this is a scheme that overrides every exercise in statistical analysis. Okay? That's what you learn in Statistics 101, 201, 203, and so forth. And this constitutes, unfortunately, the main quantitative training of researchers today. But we're not, who is interested in properties of this kind of oracle, in descriptive properties? We want to understand how nature works, and primarily we want to find effect, to predict effect of interventions, of actions, of programs. Okay? What is intervention? It's a certain changes in the environment. I take students and I pass them through some training program. Okay? They have gone into some experience that they didn't have before. That's a change. Okay? So let's go to the real stuff. The real stuff is when you have data coming up from a joint probability, P. But you perform a change and you want to find the impact of the change by inferring properties of P prime after the change. That's what the income of the students that went through your training program. Okay? Oh, here's an example. Find out whether, or infer whether customers who bought product A would still buy A if we were to double the price. So here you have a change. The sales manager of a company wakes up one morning extremely greedy. What if we double the price? Well, why can't he infer it? Because the data was taken from 50 years of company record. You can find how the price varies with sales under the history of the company, where price was determined by another sales manager or by a certain strategy. Always track the competitor. always track inflation, or by certain considerations which don't exist today. Today the guy woke up with a greedy mood, and he wants to find out what will happen if we were to double the price. So you cannot infer it from the data because the price was never varied by whimsical urges. How do we do that? That's an example of an intervention. The idea is to find out how P prime is related to P. If it was completely different, then we wouldn't be able to solve it, and we just say we can't. Everything can vary, everything can change. But we assume that certain things remain invariant. And this is indeed the definition of causality. Is inferences under change, and causal model is a symbolic system that encodes the invariance. What remains constant? That is a causal model. Once we know what remains constant, we can infer the property that we want on P prime. Okay? We know one thing is about the P prime. The price is going to be double. Right? But that's not the only thing. There will be other things. It's not the same as conditioning on the price being double. That we also know, because conditioning doesn't work for intervention. If it worked, then if it were the same, then curing symptoms will be the same as curing diseases. But it's not the same, right? You know, you're with me, right? Conditioning doesn't work for intervention. If it were, then you would manipulate the barometer to prevent the storm. The two are correlated, but they do not stand in causal relation to each other. Okay. Simply, P is an oracle that doesn't contain information about how it's going to change as a result of how one property is going to change when you vary another property. You can vary the mean without varying the variance. You can vary the median without varying anything else. Okay? So P itself doesn't contain information of how it's going to change as a result of an intervention. It contains information how it's going to change as a result of observation. That's beautiful about P. It's a very powerful device. You know, if you observe any evidence, okay, and if evidence is part of a definition of P, then you can condition on the evidence and find out how your beliefs are going to change as a result of this observation. So P is a powerful oracle for observations, but it doesn't contain the information about intervention. So you have to have additional assumptions here. These assumptions we call causal assumptions. What remains invariance. Okay. And that already defines a dichotomy between causal notions and statistical notions. I put them down with some examples. Here's a definition now. And if we have an earthquake now, and I don't manage to finish the lecture, except for this one, I find my trip here to be worthwhile. Because it's all nobody confused. Here's the definition. A statistical notion is any notion and any concept that can be defined in terms of a joint distribution of observed variables. Regression. If I give you a joint distribution, can you compute the regression coefficient? You can. Can you find that things are dependent or independent? Just look if the product equal to the joint, right? Easy. Conditional independent, the same thing. Okay. Odds and risk ratio, give me distribution, I'll compute it for you. Collapsibility, if you want to be really sophisticated. Granger causality, propensity score. Is it causal? No, it's statistical because it defines the conditional probability of a treatment giving some predictors. Statistical. Look at here. Here are notions which cannot be defined in terms of joint distributions. Yeah. Spurious correlation. If you find correlation, do you know if it's spurious or organic? No way. Okay? Randomization. It's true that every statistic textbook contains a chapter on randomization. It is not a statistical notion. Proof, help me prove it. If I give you a binomial bivariate normal distribution and with two variables, okay? I tell you, one of them is randomized. Can you tell me which one? X and Y. No way, right? So it must be on the left-hand side. Okay? If you cannot tell it, cannot test it using the distribution of observed variables, then it's not part of statistics. You need additional assumptions. And we know that randomization indeed involves intervention. How do you randomize experiment? You take subject, you flip a coin, send some subject to smoke, some subject not to smoke, and you force them to smoke whether they want to smoke or don't, right? So you intervene on the subject to behave according to the experimental protocol against their natural inclination. That is why randomization is on the left-hand side. Confounding, I wouldn't elaborate here. Many people think that confounding is a statistical notion. I have a chapter in my book saying why they are almost right, but basically wrong. Confounding cannot be defined in terms of statistics. An instrumental variable, until today, last week, I got my paper reviewed by some reviewer, and he said, you have to explain why instrumental variable is not statistical. Until today, that's 10 years after the appearance of my book. It's tough. Well, I decided to quote this reviewer in all my lectures. So in case he's in the audience here, he or she should be embarrassed. Okay, strong exogeneity, explanatory variable. An example of things that that appear frequently in our language as we talk in a cafeteria. Sometimes they appear also in publications, but they are not statistical. Now, because there is such a clear cleavage between the two, and because these cannot be defined in terms of statistical notion, it means that if you would like to do a study whose conclusions are causal claims, if you want to get causal conclusion, you must have some causal assumptions in the input. You cannot have causal conclusions just from statistical assumptions and data. Give me an example of statistical assumption, normal distribution. Right? The typical one. Or independence. I assume that X is independent on B given C. Okay? It's not enough to have such assumptions plus data to give you a causal conclusion. You must have these ingredients, causal assumptions, because only those encode the invariance. Okay, you might say, I'm willing to take causal assumptions in. This is one of the mental barriers, because you have to rely on judgments. Where do they come from, the causal assumptions? Either from our understanding of how the world works, and I have in my abstract an example that the rooster crow does not cause the sun to rise. We all agree with that. Or you conduct experiments. If somebody conducts experimental studies and comes up with the conclusion that a certain drug is effective in preventing certain disease, then this causal claim can be used in your study as a causal assumption. You rely on the finding of another study, experimental study, it becomes now an assumption. Or you can tickle the rooster, okay, and conduct randomized experiments. Okay? On a certain days you tickle the rooster and see if the sun rises, and other days you don't tickle the rooster, or something like that. Anyhow. So you say, I'm willing to accept judgmental causal assumptions in my study. I grant you that the rooster crow does not cause the sun to rise. I'm going to use it together with data to get some other conclusions. Okay? How can you articulate it? I challenge people to write down a mathematical equation for the sentence, the rooster crow does not cause the sun to rise. Unfortunately, we cannot do it with the standard language of statistics. proof, if you were able to write it down in the standard level statistics, then it will be definable in terms of a joint distribution, right, of observed variable. But we just called it causal, so it cannot be defined. So no way, no way you can write down your assumption in the language of statistics. That's what was a challenge. How do you write down the rooster crow does not cause the sun to rise? I cannot say they're not correlated, they're highly correlated. I can even put the time and say one comes before the other. Right? But I cannot say it in the language of probability calculus that the rooster crow does not cause the sun to rise. I have to invent a new language. And this is the second crisis, the second barrier, mental barrier. People hate to adapt to new notation. But it has to be done. So anyone who wants to stay within the language of statistics and do scientific studies, causal studies, they're all causal, right? Any quantitative studies in psychology, sociology, education, economics, okay, must learn a new language. That's my conclusion here, and it's not only my conclusion. You find out that such a language, you have been using it unwittingly. Here it is. Structural equation models. Okay. It's a new language. It was invented by Sewell Wright in the 1920s, path diagrams. It was picked up by economists in the 1950s and 60s. Okay. That language is a new one because those arrows that you find in the diagrams are symbols. They have as much respect, the command has much respect as your x and y and beta and alpha. They are just a symbolic system. Many have used them. Many researchers use them without knowing what they are doing. Many are still using them without knowing what they are doing. But I don't want to blame anyone, because it's very easy to use them without knowing that they constitute the building block of causal theory. And then there are counterfactuals. It's a new language invented by Neiman in the 1920s, and it has a subscript. Dan Rubin spoke here last year, and he is using this language. You see, y sub x stands for the value of y had x been equal to small x, had the treatment been given, okay? And y is the outcome. So you talk about the potential outcome that a person would have if he or she were treated. Okay. It's a new notation. Take a capital letter and put a subscript under it. It doesn't appear in Kolmogorov axioms for probability theory. It doesn't appear in probability 101. It's a new notation. Two ways of treating that new notation. One is like Dan Rubin saying it, we call it as variable, like any other variable. Sometimes you observe it, sometimes you don't observe it. So you have a missing data problem. Okay? That's one way of looking at it. Another way of looking at it is look at it as a new syntax, like a computer scientist looking at a new programming language. Right? Y sub x. It demands to have a syntactic rules, semantic rules, axioms, and treat it nicely like it deserves. And that's what it was done. Similar work was done by Lewis, a philosopher, in the 1970s. Okay? And I'll show you some of his work. He wrote it in this way. If x were true, no, okay. Y would be true had x been true. Y would be true had x been true, and put a square in between to designate it as a counterfactual, not material implication, if x and y, but in a subjunctive mode. Okay. So you have now languages, and we'll see first I want to claim that that the science, the language of science is the language of counterfactuals. So if you have taken physics 101, you have been doing counterfactuals. Take, for instance, Hooke's law. Hooke's law is the ratio between the proportionality between the length of a spring and the weight that you hang on a spring. It was one of the first law in physics in 1675, I believe. And the idea is that you write it like that. Y is equal to a constant time x, the weight. Okay? And I claim this is a counterfactual, and I prove it to you. This is just not ordinary equations. It's a counterfactual equation. Why? Because from that you can infer what y would do, what the length would be for any x, not only the one that you observe now, not only for 1 kilogram, but for any x. Okay? So it looks, even for x's that contradict the current x. Right now I hang 1 kilogram, but I can tell you what the length of the string is going to be if I were to hang 20, and I just said where to hang, counterfactual. Okay? Okay. So it gives you information about many possible weights that you can hang there. Okay. Compare this to that. This is the solution for these two equations, right? Okay. According to the definition of algebra, two sets of equations are algebraically equivalent if they preserve solutions. That allows you to move terms from one side of the equation to the other because you preserve the solution. Right? Now, are these equations equivalent to that? They preserve solution, correct? But they're not the same. These convey more information than that. From here, I can tell you what the length is going to be if I were to hang 3 kilograms, not 1. From this, I cannot tell you. You see the difference? Even though the solutions are the same, the information that this contained is richer than you have information on the right. Therefore, these are not equivalent. They are equivalent algebraically, but not equivalent in terms of information content. This contains more information. What is information? Counterfactual information. It tells you how to figure out what the length is going to be for any weight that you're going to hang there. How do you do that? Well, let's wait for that. My conclusion is that most of the equations in science, in physics, are counterfactual equations because they relate to any x. Thermodynamics, particle physics, they're all counterfactual equations. And we all learn it in high school. Okay? Only when we come to college and we come to graduate school, we have to relearn counterfactuals with a subscript there. Why? It's already there. You have counterfactual information right there in the equation of physics. Okay. Now, how do we do that? We reason now in our mind. If you tell me the x is equal to 3, I just substitute here 3, and I have that y is equal to 6. Very simple, right? In your mind. A robot cannot do that. A robot will say, hey, I get a contradiction. X is equal to 1. What do you mean x is equal to 3? It contradicts one of the equations. So what do you tell a robot to do? To wipe out this equation and replace it with a new observation. Now the weight is 3. Okay? So you see already that it is not an operation that you learn in high school algebra. In high school algebra, you were not allowed to cross out equations from a system of equations. The real connective here is an assignment connection, not algebraic equality. This is the precise formulation of the physical law. Or if you want, you can put it an arrow there. It's different than equality. Now it already looks like a graph, and that's what I'm heading at. But notice that to do that, I had to wipe out this equation because it will come out later on as a definition of counterfactual. Now we are ready to do things correctly. We don't have to rely on one oracle. We really rely on, our oracle that we rely on will be a data generating model. Okay? What is a data generating model? It's a collection of laws or mechanisms that decide for each variable in the domain which value it ought to take. Temperature of this object is going to be 23 degrees. Okay? There's some mechanism around it in the environment that looks at the pressure and various things and decides that the temperature here is going to be 23 degrees. There's a certain mechanism that decides that a patient will be cured. Okay. Very complex, but it still depends on a number of variables. So M is the strategy by which nature assigns value to the variables of interest in analysis. And the lessons of that will be we have to think nature, not experiments. And this would make it different than statistics. Statisticians constantly ask, how do we measure that? What's your design? Okay? Forget about the design for at least half an hour. Later on, we'll get to how do we measure it. But we must if you want to do causation, you must transfer your thinking into nature. What's going on in the world? Think nature, not experiment. Everything will fall into place. Later on, we're going to ask, can we measure it? Do we have enough information? Can we estimate it? Is the estimator consistent? We're going to ask all these nice statistical questions later. But first, we have to think about nature itself. Here's an example of a causal model. Every variable here is assigned a value. What's nice about it is that it can answer interventional and counterfactual questions with no difficulties. If anyone is in engineering here, has an engineering degree or engineering training, every engineer can look at that and tell you not only what the output is going to be for given input, but also what the output is going to be for given intervention. If I were to replace this AND gate with an OR gate, an engineer can predict what's going to be output. If I were to, I can tell you what Z is going to be if Y were 23. How? Engineer can envision connecting that point to a power supply with 23 volts and figure out what's going to happen. So you see, this simple device is a symbolic system, enables you to answer interventional and counterfactual questions, all with what? Just symbolic description of functions. What is the trick here? The trick is the assumption that when you vary one thing, the rest of the gates remain intact, are not touched. If I change this, the other gates remains what they were before. That is a encoding of invariance. So we have a collection of mechanisms here. We make a change in one, but we assume that the others do not change. Okay? So the point of causal modeling is to encode the invariance. And this does a very nice job. It's a tremendously powerful device because it can answer 3 billion counterfactual questions very parsimoniously. Okay. Once we get over that, I'm generalizing it now. Why should there be only logic gate? Why not any general functions? So imagine that you have inputs, background variables, some call it exogenous variable, inputs. You have variables whose values are assigned by other variables in the system, so you can explain why they attain their values. Those are unexplainable. Weather, war and peace, price of beans in China. Okay? It's not part of your study. Okay? They are external variables. They vary on their own. You don't care to ask why it happens, why the weather change, unless you are doing a weather forecast. Right? Okay. Now, you have a collection of functions. That is a working horse of that. Every variable attains a value which is a function of other variables in your model. That's all we need here. So now you have a causal model. And if you want to be really sophisticated and you don't know the inputs, you put a probability on the inputs, and now you have a stochastic causal model or probabilistic causal model. And P of U, because of this functionality, functional mapping induces distribution over all the variables, endogenous as well as exogenous. That's all there is. And that was going to be the new oracle that is going to replace the joint distribution on observed variables. So statistics works with an oracle of joint distribution. Causal modeling depends on that kind of oracles. It's much more details. And now immediately at this point I get 5 people raising their hands. How do you know the functions? And how do you know the U's? And how do you know the P of U's? And all kinds of questions. Wait a second. First, let's go through an exercise of make-believe. If we were to know all the functions and all the U's, okay, would we then be able to answer the questions? That's the first step. Science is an exercise of make-believe, constantly make-believe. I make believe now that if I turn my head, Scott is still there. The fact that I see that doesn't prove what my assumption, but it's a very nice and working assumption that helps us go through life and predict things. Okay. So here I'm going to a make-believe exercise. Assuming that you have all the functions, all the details, okay, let's define things in that make-believe world. Then we're going to ask the question, which is the hard question. I don't have all the functions. All I have is data. All I have is some qualitative constraints over that. Okay? Can I then identify my quantity of interest? Identify means I can estimate it consistently from data. Can I then do the thing that I really want to do? But first we define things in that domain, rich. It's a very rich, detailed domain. If you can define things in that domain, then you can ask the harder question, whether you can learn it from data, whether you can estimate it and all kinds of. But first is that. Well, you think it's easy, and unfortunately, very few people go through that. Let themselves be carried away in this make-believe world and go through that exercise. It's against the grains of what we learn in college. You know, don't talk about things that you cannot observe. I say, yes, do talk about things you cannot observe. I know ahead of time I'm never going to find these functions. But I want to imagine that they exist and they connect the variables. Just this exercise of imagining that there exist such functions enables me to answer questions that other people will not be able to answer if they didn't go through this make-believe hump. Okay. You have to, I'll demonstrate that. Typical example, if these functions are linear, then you have linear structural equations like the one you are used to. Okay, it's a typical example. But notice these are structural equations. These are not regression equations, and I'll talk about the difference. Now let's take some examples how a graph emerged from that. Whenever you have a collection of functions and you don't know their form, all you know is who affects whom, you have a graph. Like here, for instance, supply and demand, or supply and quantity. The price is determined by quantity and by wages. The quantity by price and income. You have a graph. See, those the elements on the right-hand side are the parents of the fellow on the left-hand side, on the dependent variable. These are independent, they are dependent. You have a graph. Here, I and U determines Q and P, because they appear on the right-hand side. So I put arrows between them, and you have a graph. Okay? If, assuming now that the government wants to impose a price fixing on this commodity, what is going to happen? Well, let's see first the definition of intervention. We have a set of variables. Let's define an action, do X, by simulating the action of fixing X to a constant. What does that mean, to fix X to a constant? It means to dislodge X from its current influences and subject X to the power of your muscles when you do X. If government decides to fix the price, then the price will no longer depend on the wages and U2 and the quantity, but depends on the government decree. Here you are. Okay? Government comes here, you should charge no less, no more than P0. So no longer the previous variables play any role. What does it involves? Wiping out an equation and replacing it with a constant. So here we simulate the intervention of fixing or setting a variable to a constant. Right? Like we had before with the spring. You wipe out the equation, replace it with a constant, and that simulates the intervention do x. We form what I call the mutilated model with one equation missing. If x is a set, you have several equations missing. Okay? And now you have a new graph, you can solve it, and this will answer your question about what the quantity will be if government were to fix the price at P0. You solve these two, you have P0 here, you find it here. Easy. But in general, we can define a counterfactual. Now, we can say, first notation, y sub x of u equal to y will be the sentence. Y would be small y in situation u had x been small x. Complex sentence, right? It's we call it counterfactual. We think, ooh, it's imaginary, it's mystical, because you cannot measure it. But it's simple because it has a very simple definition. What is the definition of that sentence? It means you form a mutilated model with the equation of x removed, you replace x with a constant, small x, and you ask whether the solution for y is equal to small y. Then if it is equal to small y, then this sentence is true in the model. So you see now we have reduced the complex and mystical notion of counterfactual by high school algebra. Solve an equation with one equation replaced by a constant. No more mystic. That's the second most important part I want to leave here. Counterfactual are high school algebra. Very simple. And because of this is simple, the whole causal inference business is just friendly and easy. And this is the fundamental equation for counterfactual. Y sub x of u is equal to the solution for y in a system of equations after you remove the mutilated by the equation that previously determined x, now it becomes a constant, find the solution. It's true that we were never asked in high school to remove equations and then solve it. It's an operation that we did. That's why it's non-algebraic. Okay? But it gives us the semantics for counterfactual. And whereas my colleague Dan Rubin takes that as a primitive, I take it as a derived quantity. If you start with a set of structural equations, then the counterfactual is derived from a structural equation. All of you that are doing structural equations are dealing with the machinery of counterfactuals. You can define it, you can derive it, you can derive consequences of it. You can find even more important things. Look what I can do. Hey, Mao, no hands. Look what I can do. You can define joint probabilities on counterfactual. It's something that certain statisticians resist very vehemently. To find joint distribution on counterfactual that may conflict. I say here that what's the probability that variable y would attain the value small y had x been equal to small x, and simultaneously variable z would be taking the value small z had w been equal to small w. What about if x is equal, it contradicts with small w here, okay? You have a contradiction. How can you find probability distribution on contradiction, okay? It's not a contradiction, because these are models mutilated in different way. Here I mutilate it by removing x, here I mutilate it by removing w. And I solve it in one room or the other, and I check if the two solutions match the requirement of small y, small z, and I can put probability on the input that leads to such a consistent solution. And I sum all the probabilities, I have a definition of a joint counterfactual. Once you have a definition for a joint counterfactual, you can do onto counterfactual what you do to normal variables. You can define independence among counterfactual, conditional independence, all the things that people like to do and don't know what they're doing, just thinking mechanically. You can derive them from your structural equations. I can tell you the probability of a joint counterfactual. Give me any structural equation, assuming that you have all the equations there, all the parameters defined, specified. And I can find it. If you don't have them, comes the question, under what condition can we learn them from data? Here's an example of something that, definition of the probability of intervention, of the result of intervention, same thing. Here is a counterfactual that looks contradictory. Mr. Joe, okay, is alive and he took a drug. What's the probability that he would be dead had he not taken the drug? Yeah.
Earlier, when you were talking about the joint probabilities of counterfactuals, let us say you mutilated the graph in one way, and you mutilated the graph in the other way, and those two ways are not, they both can never exist at the same time. Would you say that the joint probability would be zero?
No.
Yeah. So per that definition of what that is, even if those two mutilations can exist at the same time, that it's
No. You solve it in two different rooms. One room you have mutilation on X. The other room you have mutilation on W. You ask, Joe, what did you get as the result of a Y? Tells you, I got 5. Shmo, what did you get for the answer for Z? It tells you 3. He said, this is what I want. I ask, what's the probability that Y will attain the value 5 and X will be equal to 3? It's fairly consistent because I did it on 2 different mutilation in 2 different rooms, and I got an answer that I required. And I have a probability distribution. Why? Because I have a certain input that will give rise to this solution in this room and this solution in this room. Okay? So although they cannot happen in real life at the same time, okay, but they could, the 2 solutions can occur under 2 different mutilations at 2 different rooms at the same time. Solving equation is an event. Then you have here a probability on joint event. But the event here is finding a solution for Y in one room, finding a solution for W or whatever in another room, like a joint event. And they're not contradicted because you are doing different mutilation. In real life, I could not do the mutilations suddenly, but I can ask the question hypothetically. Here, look at the answer here. It's a simple, very simple query that comes again and again. It's called the probability of causation. Let's say you have a patient here that died, that's Y, and he took a drug, X. So we know he died and he took a drug. The question is, would he be alive had he not taken the drug? Okay? So I find the probability of Y equal to Y prime, okay, which means alive. This is die, and this is being alive, had they not taken the drug. This contradicts that, right? X contradicts X prime. But I can ask this question, because this involves a mutilation. Given that the solutions for X and Y are small x and small y, okay, what's the probability if you have to mutilate the model, mutilate the equations, under X, you find that Y is equal to 0.
Kind of allowing you to look at all
possible worlds.
All possible worlds.
Absolutely, yeah, you got it. Philosophers like to talk in possible worlds, right? But here we're talking about options available to you. Possible worlds that you are in control of, at least theoretically, hypothetically, had he not taken the drug. Okay. Once you have joint probability on counterfactuals, you are almighty everything can be derived and done. Yes, sir.
Maybe we can come up with several structural models to describe a certain situation. Can
Maybe.
we use these things?
But I can do it with one. Why should I think about several structural models? Yes. If I'm not sure about my model, of course I'll have to consider several possible models. But I'm sticking to one. What can you do with one? A lot of things that we didn't realize we can do.
Compare the one with others.
Different question. Let me first explain what you can do with one structural model.
So the sum on the previous page, the sum is the sum over all possible worlds, is what you're saying.
The sum is on, here is on the sum of U. U is not exactly world. World is a combination of U and V. So all assignment of values to all the variables in the system. That's a world in this philosophical sense. I will skip over the philosophical stuff of Lewis, which has to do with the closest world. That's a definition of counterfactual in the philosophical literature. It's identical. I can explain my definition of structural equations in terms of operation on possible worlds. But let's skip that, because I want to get to mediation. This operation, or this definition, can be fortified with axiomatic characterization. This is a list of axioms which the counterfactual must satisfy, and they are complete in the sense we haven't forgotten any. Logician can prove completeness. Okay. And you can do a derivation then. If you have assumption in the form of counterfactual, you can apply those as inference rule and get new counterfactuals. That's the logic of counterfactuals. But let me go to something which I think very important, which is the difference between structural equations and regression equations, because I keep on seeing that confusion in the paper that I review, and it saddens me. So now that we understand what structural equations are, and they have really a counterfactual meaning, we can tell the difference. Regression equation is claimless. When you write down an equation like that, then before you determine the value of A, you haven't made any claim about the world. Everything can happen. All you proclaim now is, I want to estimate Y, and I want to find the best estimate of Y given observation on X. That's all you claim, your desires, okay? But nothing about the world. When you write down a structural equation, you claim something about the world outside you. Okay? You claim, for instance, that the expected value of Y, given that you do X, you set its value to something, is going to be only a function of X. B of X is not going to be a function of any other manipulation in any other variables which may be in some other equations in the system. So imagine this is one equation among 200. And the 200 equations involve X and W and others. By putting down this equation, you made a claim that if you manipulate X, Y is going to change only as a result of X. Or if you manipulate X and any other Z, okay, Y is not going to change. This is a very important thing to distinguish. We're making an empirical claim. It's falsifiable when you put down a structural equation, because you can conduct experiments and find out if it's true that wiggling X will not change the expected value of Y once you set X to a constant. It's a basic definition between the two, and the mixing between them leads to all kinds of equations. For instance, when would B equal to A? We have a criterion for when. I'll show you in a second. Okay? Or question of when is B estimatable by regression method? We have a criterion. All this is part of the theory. But first we have to understand what the meaning is of a structural equation. It's a statement about intervention. It's really a statement about counterfactuals, which is more detailed than intervention. An individual, Mr. U, will react that way to manipulation of X. Now that we got this under control, let me make a statement about the methodology that comes out of that. In every qualitative studies, in behavioral and social sciences, must go through these 4 steps. Define. Define your quantity of interest. What are you after? And this is the most neglected part of many of the studies that I see. You start writing an article and you didn't define what your target quantity is. I would like to see, for instance, you said my purpose is to study the effect of drug A on recovery type B, or effect of a training program on the population, on the earning of future earning of a certain population. Okay? That is very important. I proved to Scott today that people are doing mediation, all people are doing mediation, without defining the quantity. What they are the way they define quantity is by the estimator that they hope will give them the quantity, but not by the quantity itself. Now, what does it mean to define the quantity? You go to your model. You assume that you have this Santa Claus, or this oracle, structural equation, fully specified, with all the U's and all the parameters. Okay? Would I be able to find the answer to my question, to my quantity, had I have all the parameters specified? That's what it means by define it. Okay. So the input is going to be a model, the output is going to be a number for your quantity. It's an algorithm. Second step is to define your assumption, articulate your assumption. And we talked already about it, that every study in causal reasoning must begin with assumption. The claims are only as good as your assumption. Therefore, you have to express them in a language that will make your assumption transparent. I'll show you some non-transparent languages. I recommend using graphs as a language where your assumptions are transparent. Your colleagues can look at your graph and discuss whether your assumptions are plausible, whether you've forgotten a variable, whether additional assumptions are warranted, and so forth. Right? And indeed, most of my work has to do with long graphs, because it's easier, because many of the conclusions can be obtained just from the graph, with not making any assumptions about the form of the functions in the structural equation. So I leave them totally non-parametric, not making any distribution assumptions about the exogenous variables, about the noise variables, okay? Most of the results can be obtained directly from the graph, namely as close as possible to where the assumptions are generated. And they're generated in your mind. It are judgmental assumptions. They are based on your understanding of the physics of the problem. I like to be as close as possible to the source of your assumptions. So when anything goes wrong in the derivation, you can correct it, because you're close to the scientific knowledge. Then comes the exercise of identifiability. Find out if Q, as defined here, is identifiable. Namely, if it can be estimated consistently from observational data, if you're doing observational studies, or from experimental, or combination thereof. And then estimation. I wouldn't spend any time on estimation, because statisticians are better than me in doing it. I cannot contribute much there. Here's an example. How are you doing on time? Almost done, huh? No, I'm going to go to mediation, I promise you. Let me go quickly over that. Just show you that you can flip in different quantities here, which have a name. Like here you evaluate a policy. Do X and do Z and do W, okay? It's a policy of treatment over time. Okay. Look how I defined it. It has a very clear definition. You give me a model, give all the functions, I can give you a quantity. This is what it thinks of. You don't have the model, If they want a partial specification, I can go to the next step and make assumptions and see if they're identifiable. But that's the first step. So let's go into the first task. Find effect of intervention. The problem is predict the impact of proposed intervention using data obtained prior to the intervention. We know that the solution must be a policy claim on the basis of data combined with causal assumptions. We have mathematical tool for causal assumption, and now we have to decide whether the assumptions are sufficient for obtaining a consistent estimate of that quantity, which is the prediction under intervention. The nice thing about this theory is if the answer is no, but if the answer is yes, then it gives you an expression, a closed form expression for the quantity of interest. And if it's not, then it can suggest measurements or experiment that, if performed, would render a consistent estimate feasible. This is the quantity, P of y given do x. I would like to compare two languages or three languages for articulating assumptions. First, English. We're all familiar with it, right? Here's the language, English. Assuming it will have to decide the effect of smoking on cancer. We understand that smoking goes through an intermediate state by accumulation of tar in the lungs. Okay? It causes that. And that can cause cancer. We also are suspicious of the fact that whatever correlation that we might find between smoking and cancer might be confounded by a genotype that makes people crave for nicotine and at the same time puts them in cancer risk. Okay? That's a story I gave you in English. I just finished 2 sentences. We understand what it is. We have to evaluate the effect of causal effect. There's no other effect except causal effect. So excuse me if I just say effect of smoking on cancer, given a possibility of confounding through a genotype U. Okay? I described to you the story in English. Okay? You understood it. Your colleague understood it. Okay? Okay. Now you want to go to a formal language. Okay? Here's one possibility. It's called the potential outcome framework. Dan Rubin spoke to you a year ago. This is how the assumption, the story, going to look like if you articulate it in the language of potential outcome, any counterfactual. For instance, this will be the fact that the tar accumulation is a function of smoking. It's not a function of the cancer. So y, which is the output, the cancer, is not a determiner of the tar deposit. That's how it looks in the language of potential outcome. All these are subscript variables, which means they are counterfactual. Here you have conditional or independencies between a joint counterfactual and a counterfactual. Okay? This is encapsulation of the English sentence that I gave you about that. That's one way of articulating in the formal language. But I give you a third possibility, which is my preference. Here it is. Okay? So these 4 lines of equations, which are very hard and not too friendly, and we don't know if they are consistent, we don't know if they are complete, we don't know if they are redundant, okay, are encapsulated in this graph. They're equivalent, formally equivalent. I can take that and write down that. I can take that and write down that. Okay? I think it's more friendly. And this is one advantage that structural equation has, as opposed to the Niemann-Rubin potential outcome formalism. Okay? It's easy to articulate assumptions. It's very important to articulate them in a transparent way. I explain to you why. Because you want it to go through a through scrutiny of your colleagues. It has assumption here. For instance, such assumption that genotype is not affecting the tar independently. Tar is only a function of smoking. Identifiability is defined formally, and what identifiability means is that exactly what we talked earlier. I don't know the functions, and I don't know the probability on the use, and I'm asking under what conditions the details of the models won't matter. That is the idea of identifiability. When can I identify the desired quantity from data alone plus the graph? I know the graph structure, not annotated by any functions. Okay? If I can take this pair and come out with my quantity, the target quantity, then the details of the models won't matter. So that's the question of identifiability. Any questions about that? You ask about how we're going to find the functions. Under certain conditions, we don't need the functions. Here's an example, confounding. We talked about that. You have to find the effect of X on Y. And you have a bunch of attributes there. For your count is to participate, count is to don't participate. Okay? You have economic, social economic conditions, genotypes, all this business. Okay? Some of them affect the treatment, some of them affect the outcome, some affect each other. Okay? And you ask under what condition the effect of X on Y can be consistently estimated from the data without knowing the functions, without knowing the distribution of the errors, just looking at the structure. And the answer is yes, there is a simple criterion. It's called backdoor. And if, here's the solution, if there is a set of confounders, of observed confounders, that separate X from Y, separate all the backdoor path between X and Y, then they are admissible for adjustment. Then you adjust for them and you get the desired policy evaluation, effect of X on Y. Okay? It's given to you in the famous adjustment formula. You condition on both X and Z, the set of covariates. Okay? You average over Z, and you get what you ask for, the effect of X on Y. Yeah, go ahead.
This may be a strange question. In
No
these
question
types,
is strange.
in these types of causal graphs,
Yes.
is it possible to have a loop?
Yes. As I showed you, I started with a loop in economics, right? Price determines the quantity, quantity determines price. Yeah. The backdoor formula that would not work for loops, not only for that. But the entire theory works for loops. Yeah. Good question. Okay. So you have a graphical criterion that you look at the graph and you said, yes, this set of covariates would be sufficient. If I can measure them, I can adjust for them, and I'm guaranteed to get my results with no bias. Assuming, of course, that the graph structure is correct. If your graph structure is incorrect, like for instance, you forgot the link between Z1 and Z2, then your answer is going to be wrong. Okay? But at least you can discuss your assumptions with something which is transparent, meaningful, cognitively meaningful. Okay. This is on that basis, okay. We have an extension for that. Sometimes you can find the causal effects with no adjustment, with some, or double adjustment, or all kind of tricks, which necessitate not only finding a covariate set and adjusting on them, but more intricate kind of analysis. Okay, and there is a general criterion today, a graphical criterion that tells you under what condition you can do that. This is something which is surprising. Okay? Suppose you cannot measure any of the confounders here. not Z1, Z4, Z2, you cannot measure them. They exist there, and you cannot touch them. They're hidden. But you can measure that fellow. Okay? The answer is yes, you can still identify the effect of X on Y. And there are all kinds of graphs and subgraphs that allow you to do that, and we have a calculus. Here's an example that I got from a sports physician concerning about the effect of warm-up exercises on injury. And you have here a graph that tells you various measurable, and some of them may be unmeasurable. And the question is, which one are sufficient for adjustment? Are sufficient in the sense that you can get the correct causal effect unbiased. Okay? Here's an example. The parents of the outcome are sufficient. Right? They obey the backdoor criteria. No. Previous injury is a bad one because it is a collider. What does collider do? If you condition it, it connects a back door here. Zoop, zoop, zoop. No good. Here's one which is not very well known. How about the parents of X? It looks like they disconnect all backdoor paths. They're correct, but you have to watch out because among them there could be an IV, namely an instrumental variable, in which case if you left any confounder unobserved, you adjust for an instrumental variable and you amplify instead of reduce the bias. It's not very well known, it's just a new result by Wooldridge, which I amplified in the paper I showed you. What about that? It turns out, yes, it's a graphical condition that it's part of the theory. Okay. But anyhow, we have now graphical criterion. You look at the graph, you can tell me I can only observe a subset of things. Is it sufficient? And the answer is yes or no. It's an algorithm. Okay. I want to jump to mediation because that is also a topic which is sorry, here's that's a good one, the propensity score. We go to estimation now. Same graph, okay? You have 1,000 variables here. Very sparse data. You cannot really adjust for all the variables that you need because you're going to have many empty cells. That's the idea of propensity score. Instead of that, you are looking for a function of the variables. Okay? If you find a function of particular kind, you can adjust just for that function, just L, and instead of, you get an adjustment on a scalar variable instead of a multidimensional vector. That's a propensity score. It turns out that if L is equal to the probability of X given those, if this is you take it as a function, then it's adjusting for L is the same as adjusting for the Z's. Okay. Now, which means that if you select for the Z a sufficient set, then L would also be a sufficient. But if you select for L something else which is not sufficient, or which introduce bias, then L will be as screwed up as your bias. So the asymptotic bias of propensity score is equal to that of ordinary adjustment for the same Z. The propensity score does not, including additional covariance in the analysis, can spoil the bias reduction potential of other variables or other covariance. For instance, if you introduce a collider, that can spoil things. Choosing sufficient sets for propensity score requires knowledge about the model. You cannot choose things correctly unless you have the graph or at least some properties of the model itself. Okay? And here's an example which I present. Which covariates should you adjust for? Say you want to find the causal effect of treatment on outcome. And you have here hygiene, assignment, some observable which is an effect of both, age, B2, a follow-up after the outcome, It turns out, well, if you do things by the backdoor criterion, you should adjust for age. You should not adjust for B1 because you're going to collect a collider here. You should not adjust for assignment, even though assignment is a good predictor of the treatment. Because if you, because of this new paper, okay, that holding an assignment fixed amplifies the bias caused by unobserved confounder, unadjusted confounders. So all this can be done by just looking at the graph. I want to go now to mediation because we talked about it. Gee, I have so much material. Bing. It's amazing. Did I expect guilty with probability 1? It's chapter 9 in my book, so. Mediation, or effect decomposition. Why decompose effect? What is the definition of direct and indirect effects? And what is the policy implication of them? And when can they be inferred from experimental as well as observational studies? Okay. 3 reasons why you want to look at the decomposition. First, to understand how nature works. Yeah. And that's why the paper by Barron and Keeney got 17,000 citations. 17, one of the most cited papers in the history of quantitative methods, right? Because people are interested to know if things are caused directly or indirectly, and if indirectly, through what variables, because you might do something about those other variables. Sometimes legal requirements behooves you to estimate direct effect and not indirect effect. And then I'll leave the rest. Now, what's the difficulty here? Let's look at the effect of hiring discrimination. Sex bias in hiring, okay? The law says that employers should not discriminate on the basis of sex if the qualifications are the same. Okay? The law does not say that you should not discriminate on the basis of qualification, even though the qualification can be gender dependent. Okay? So which means that the law behooves you to estimate, if you want to prove an employer biased, then you have to prove that there is a direct effect between gender and hiring. Notice that I'm talking about effect even though gender is not a manipulated variable. That's also a difference between me and Rubin. Okay? No causation without manipulation? Forget it. There is causation without manipulation. Otherwise there wouldn't be any laws like that on the books. Okay. Now the problem with that is if you have linear model, there's no problem. You have alpha, beta, gamma. You are trying to estimate alpha, the direct effect. Okay. But when you have nonlinear, the level at which you condition Z2 will affect the direct effect in nonlinear system. So the question is, what do you do? What do you set Z to? What value? You should not just condition on Z. Because if you condition on Z, you're going to get spurious correlations coming from possible latent variables here through that collider. Okay? So the definition of direct effect could not be articulated in terms of conditioning on the mediator. I'm going to use Z for the mediator. The whole literature on mediation treats direct effect as if you condition on Z by Bayesian conditioning or just for Z. That's all wrong. You have to set Z to a constant by intervention. Set it constant. Okay. Just for Z? No. You got it. Now, what do you do in nonlinear system? This is a nonlinear system, right? Z is a sum F of X and noise. Y is some G of X in the mediator and some noise. Good. Definition of direct effect. direct effect from a certain level of x to another level, unit increase in x, okay, is equal to the expected change in y when you change x from x0 to x1, and for each u, you keep z at what constant? At a constant, at the value that z would attain before the change. Now look at what I've done now. I'm using now the language of counterfactual to tell you at what level to keep z constant. I feel free with counterfactual. I know they can be computed by high school algebra, right? That's what gives me the confidence and the chutzpah, okay, to talk about counterfactuals, nested counterfactuals, all with such freedom and comfort. I know I can compute it. No fear. Okay. So here's an example. This is an expression. This is definition of direct effect. Look at what I have here. Expected value of y. Had x been x1, I wiggle x from x0 to x1, and z is kept constant. What value? Whatever value z would get before the transition, when x was x0. It's an expression. It's an algebraic equation in the language of counterfactual, but I have no fear, as I explained to you, why, because I know I can compute it. Whether I can estimate it is a different question. I can define it now. Now it's defined for all nonlinear systems, all non-parametric systems. I don't have to decide for the function. I don't have to find f and g. And I'm asking the question under what condition it can be. Here it is. Is nested counterfactual defined? Sure. You can look at the set of equations and find out what value z would obtain before the transition. Then mutilate the equations again with the value that you got for z, with the solution you got for z. So you mutilate z, mutilate x, at two different values, and find out the solution for y. It's well defined. If it's well defined, then I can ask the question about identifiability. But first, let's go to indirect effect, because that's a tough issue. One of the teachers of the structural equation model wrote to me and said, I have a hard time explaining to my students what indirect effect stands for. We know that direct effect means you keep that constant, okay, and then you wiggle x, and that's what happens to y. But what about indirect effect? What do I keep constant? I have to disable this line. I cannot keep anything constant and disable this line. Okay? I cannot bias the fact that I cannot circumvent the fact that I have here an arrow between x and y. So how do I disable that thing? Here's a definition in terms, again, of nested counterfactual. It allows you to articulate your understanding of what indirect effect is. It's expected value of expected change in y. When we keep x constant. We only vary z. To what value? To the value that z would get had x changed. You see the tricky here? You vary z, but to what value? Counterfactually. If x were to change from 0 to 1, then z would get some value. So change z to that value. Tricky, huh? Double counterfactual. But it has expression. Once you can express it, forget about the trickiness. It's just a solution of equations. And the answer is, let's go here, that it has conditions under which you can estimate it from data. Empirical data, experimental, and also observational studies. Okay? And by the way, if you have not unobserved confounding, you have the mediation formulas. Okay? This is normally assumed in literature. You have no confounding. So look what happens to the direct and indirect effect. Direct effect and indirect effect. In the direct effect, you set both x and z to a constant. But you vary x from x to x prime. So you ask for the change of y when you wiggle x from x to x prime, holding z constant, it's under the do. But at what value? You average over the value of z, and the condition where x is set to prior to the transition. And you look at the distribution of z under that condition. That is a weighting function when you do the average of all possible value of z. The indirect effect is different. You don't find such a nice intuitive explanation, but it is a formula that can be estimated by regression if you have no unobserved confounders, because all the do operators are reducible to ordinary conditioning if you have no unobserved confounders in the graph. This Markovian model. Okay? So it's done. The mediation problem is solved because we have a graphical condition to find under what circumstances it can be identified from empirical as well as observational studies. What is that? I told you causality is simple. I presented to you a formal basis and counterfactual inference. It unifies the graphical potential outcome and structural equation approaches. Those of you who are doing structural equations, be aware that you're holding in your hand the solution to all causal questions, but you just have to do it right. That you're holding in your hand the machinery, the symbolic machinery that can provide the answers to all causal questions. It's friendly, and it gives you a formal solution to century-old problems and confusions. And as my friend said, was the Aristotle? Not really. He is wise who bases causal inference on an explicit causal structure that is defensible on scientific ground. It wasn't really Aristotle. I just wanted to draw respect from you. I put his name. It's really Charlie Poole. Wrote it in one of his papers. And the questions will be answered. Do we have time to answer questions?
You're over time, but I think if people can stay, we have the room till 1, so we can take a few minutes.
Good. I could have continued. No, it's time for you to ask the questions.
Can you use the mechanisms of direct effects and indirect effects to make statements about the assumptions in your graph?
Yeah,
Is that a way to build
very
this?
important. Very important. I have to go back. Yes, it's very important. Okay, let's look at the graph here. The graph has arrows, has double arrows, and has missing arrows. Okay? A missing arrow, like for instance here, okay, it tells you all that if I were to wiggle x, okay, then there will be no effect on y. It's in the interpretation of all. First of all, the assumptions in the graph lie in the missing arrows, not in the arrows. Arrows tell you there could be some connection there, some causal connection. I'm not sure. The coefficient can be 0. The strength can be 0. Everything can happen. The missing arrow is a statement about the world. If you were to wiggle x here, nothing is going to happen to y. If you were to randomize it, it's a claim. The assumptions, the missing link, a double arrow, it's a statement about independence of the arrow terms. Okay. It's also causal assumptions. It's not a statistical assumption because the arrow terms are unobserved. They have only meaning when you talk about causal models. They are not the residual of the regression. Okay. They have only meaning in a causal context. Therefore, a missing double arrow, which stands for independence of the arrow terms, is a causal statement about the world. It has, you can verify it empirically if you had the chance to do a randomized experiment. Okay, these are two assumptions. Did I answer your questions? So one way of looking at the graph is as an encoding of who affects whom under experimental conditions. So you have to think about, is it true that if I were to change X, nothing would happen to Y? You imagine wiggling with your hand or with some external forces, with some encouragement in social science, for instance. If I encourage students to take a history class, okay, would there be any effect on their earning capacity or things like that? Any other questions? Hey, no questions. I can continue with it.
I think this would be a good time to end. Thank you for your words of wisdom and your insights.
Great. Thank you for being so attentive.
And Professor Perl,
Thank you.
Our Urban Health Institute would like to give you this little token of appreciation for your lecture here.
Wow, thank you.
Taking time out of your busy travels. He just came from Boston this morning, got up really early to come and be with us today, and has to be on a flight soon to Florida. We're heading back to California.
Well, with such friendly audience, I'm glad I woke up at 4 a.m. today. It was worth it. Thank you.
Thank you.
I appreciate it.